welcome back to the channel. In this video, we will look at the characteristics of machine instructions. An instruction takes some operands and performs operations on them. We need two numbers and the arithmetic operation to add two numbers using a calculator. An instruction works the same way. It takes some operands and performs operations on them based on the opcode. There are four important components in machine instruction. The opcode is the most crucial part of an instruction. It specifies the operation to be performed. Common operations include arithmetic operations like addition and subtraction, as well as memory operations like load and store. Other types of operations are also available. Addressing mode determines how the operands are accessed. In other words, the addressing mode tells us where the operands are located. Operands are the data items that the operation will act upon. They can be located as a constant in the instruction itself, inside the register, or inside the main memory. Instruction format defines the layout of the instruction, including the number of bits used for the opcode and the number of operands in the instruction. Modern architectures can have 0 format, 1 address format, 2 address format, and 3 address format. At its core, the processor is the instruction set. The instruction set provides the processor's functional requirements. It is like a document with a set of requirements the processor needs to have. Implementing the processor is, in large part, implementing these requirements. The set of all instructions a processor can execute is called the processor's instruction set. Together, these characteristics determine the functionality and capabilities of a processor. Now, let's examine how machine instructions are executed inside the computer. Machine instructions go through 7 steps to perform their tasks, known as the machine instruction cycle. The first phase is the instruction fetch cycle. During the installation of an operating system, a lot of essential files, including the OS kernel, system libraries, drivers, and other necessary components, are written to the hard disk or SSD. These files contain the compiled instructions that the CPU will execute when the OS is running. These instructions are then loaded to the RAM from where they are fetched. This instruction is then stored in the instruction register located inside the CPU. The next cycle is the decoding cycle. In this phase, the CPU needs to figure out what that instruction means, essentially translating it into signals that can control the appropriate parts of the CPU. The CPU has to identify the opcode from the instruction. The CPU uses a special part of its hardware, often a decoder or a control unit, to interpret the opcode. The processor then extracts various fields from the instruction register to execute the instruction. It is difficult for humans to deal with binary representations of instructions. So, in most books, symbolic representations called mnemonics are used instead since these symbols are more readable for humans. Each symbolic opcode has a fixed binary representation. The opcode is then matched to a predefined set of machine instructions that the CPU understands, like arithmetic, memory, or control flow. Once the opcode is decoded, we enter the address calculation cycle. Operands are usually stored in registers, RAM, or as constants in the instruction. The main job of this cycle is to calculate the effective address of the operand. An effective address is the final memory address of the data. It is often calculated dynamically based on the instruction's addressing mode and the values of registers or memory locations involved. For example, an instruction may contain a register as an operand, which in turn holds the address of the data in the main memory. In this case, the effective address is the address of the main memory and not the register. The next step involves fetching the operand from the effective address calculated in the previous cycle. The process of fetching the operand varies depending on its location. If the operand is in a register, it is directly accessed from the CPU's internal register set. If the operand is in the memory, the CPU sends a memory read request to the memory controller, which retrieves the operand from the corresponding memory location. Suppose the operand is embedded in the instruction as a constant. In that case, it is directly available from the instruction, and no additional fetch is needed. After fetching the operand from memory or a register, it is loaded into a general-purpose register or another part of the CPU where the actual computation will occur. The data operation or computation phase is a critical part of the machine instruction cycle where data processing or manipulation occurs. This phase involves executing the specified operation on the operands as the instruction dictates. The ALU performs the specified operation on the fetched operands. The result of the operation may affect various status flags in the CPU's status register, often referred to as the flags register. After completing the computation, we move on to the operand store cycle. In the operand store cycle, the result of the operation is stored in the appropriate location, either in a register or memory, so that it can be used later in the program. This phase is also referred to as the write-back phase, since the result is written back into a location that subsequent instructions can use. If the result needs to be stored in memory, the CPU might need to calculate the exact memory address where it will be written. After the data has been successfully stored, the CPU prepares to move on to the next instruction in the instruction cycle. The next address calculation phase of the machine instruction cycle is responsible for determining the address of the next instruction to be executed after the current instruction has been processed. The next instruction address can be calculated in several ways, depending on the type of instruction executed. Here are some common scenarios. Sequential execution. For most instructions, the next address is simply the address of the current instruction plus the size of the current instruction. This means that if the current instruction is located at address 1000 and it occupies 4 bytes, the next address will be 1004. Branching instructions. If the current instruction is a control flow instruction, like a jump or branch, the instruction will specify the next address. For example, a jump instruction might contain a target address to which control should be transferred, altering the normal sequential flow. Function calls and returns. In function calls, the next address is set to the address of the function being called, while after a return instruction, it points back to the instruction following the call. The number of addresses in an instruction plays a crucial role in determining how efficiently a program can be executed. Different architectures balance the number of addresses based on intended use cases, performance goals, and resource constraints. In most architectures, many instructions have 0, 1, 2, or 3 operand addresses. Most architectures also have a few special-purpose instructions with more operands. For example, the ARM architecture's load and store multiple instructions have up to 17 register operands in a single instruction. Let us look at these different formats one by one. One address format is an instruction format where only one operand is explicitly specified within the instruction. The second operand is implicit and usually means the accumulator, a special-purpose register in the ALU used for storing temporary results. This means the instruction assumes that one of the operands is already in a predetermined register or memory location. In this example, load A loads the value from memory location A into the accumulator. Add B adds the value from memory location B to the value currently in the accumulator. Store C stores the final result from the accumulator into memory location C. This format is typically used in simple processors or early computers where minimizing instruction length was important. In a two-address format, an instruction uses 2 operands. One operand serves as both a source and destination, while the other is only a source. This means the operation's result is stored in one of the source operands, replacing its original value. This format is more efficient compared to 3-address formats, as it requires fewer operands to be specified, though it does overwrite one of the operands. In this example, the add AX BX instruction is a 2-address format. The result is stored in AX, which replaces its original value. BX remains unchanged with the value 3. This format is straightforward for hardware to process, making it suitable for certain instruction sets. However, because one operand is overwritten, careful use is required when both values need to be preserved. In a 3-address format, an instruction contains 3 operands, 2 source operands, and 1 destination operand. The result is stored in a separate destination register, preserving the original values of the source operands. This format provides more flexibility since no operand is overwritten, but it typically requires larger instruction sizes due to the need to specify 3 addresses. In this example, the add R3, R1, R2 instruction is a 3-address format. It adds the contents of R1 and R2 and stores the result in R3. R1 and R2 remain unchanged, while R3 holds the result. In a 3-address format, no source operand is overwritten, making it useful when the original values must be preserved. However, specifying 3 operands requires more bits in the instruction, which may increase code size. In a 0-address format, instructions do not explicitly reference any memory or register addresses. Instead, this format relies on an implicit data structure, usually a stack for operand storage and manipulation. All operations are performed using values stored on the stack, where the top of the stack holds the operands, and the result is also pushed back onto the stack. In this example, Push A and push B are examples of one-address instructions. The instruction push A refers to the value at the address of A and pushes it onto the stack, while push B pushes the value at the address of B. Add is an example of a zero-address instruction in a stack-based architecture. This is because it does not require explicit operands. Add implicitly pops two operands from the top of the stack, adds them, and pushes the result back onto the stack. No operand addresses are needed in the instruction itself. Thank you for watching the video. I hope you learned something today. Have a beautiful day, and see you in the next video.